Okay, today we're gonna go over Unit 4 AP Stoichiometry, and in this one we have a redox reaction. So we're gonna start off with labeling the charges of each of these elements. So P4 is 0, right?
Yeah.
And then hydrogen is +1, oxygen is -2. So in order to balance out the H, O, and the Cl, the charges of that, -1 and -2. So how would I balance out the -2 of oxygen? This chlorine would become a +1, right? Because +1 and then +1 and -2. So in this case, chlorine's charge is +1. And then over here, oxygen is -2 and hydrogen is +1. Okay. And then on the right side, hydrogen is +1 and oxygen is -2, right?
Yeah.
And then here, hydrogen is +1 and chlorine is -1. Right off the bat, we can see that chlorine's charge has changed. It went from +1 to -1. So when your charge is going from +1 to -1, that means that chlorine is being reduced, right? So we can write that as Cl plus 2 electrons is Cl minus, right?
Mhm.
Because the charge was reduced, which means it's gained electrons. So now this is a bit of a tricky part. We have to figure out what happened, what was oxidized. And you'll see that it comes from this part over here. So 4 times +1 for hydrogen, right? Plus P plus 4 times -2 equals 0. So 4, sorry, it should be 3. 3, let me undo that. So 3, right? Plus P minus 8 equals 0. So P minus 5 equals 0. So the oxidation of phosphorus is now 5. So you can see that phosphorus went from +5 over here, right? When before it used to be 0. So as phosphorus went from 0 to +5, that means that it was oxidized, right? So if it was oxidized, we can write that as P4 became P4 5 plus 5 electrons, right? Because it lost 5 electrons. Does that make sense?
Yeah.
So if this is so, let's erase this part of it so that we can see everything here. So now that we have our reduction and oxidation part, we can actually balance this, right?
I think
So,
there's some blocking the work.
oh, there is?
Okay. Okay. Wait. Okay. I think it's okay. You moved it to the side now. Okay. That's fine.
Okay. So in order to balance this equation, we'd have to balance out the electrons, right? So this would be multiplied by 2, right? The top one would be multiplied by 2. No, 5. Sorry. Right? Is that right?
Wait. Why are you multiplying by anything? Oh yeah. Sorry.
We have to balance
Yeah.
the
Yeah. Sorry.
So let's write all of this out. And okay. So this becomes 5Cl plus 10 electrons yields 5Cl, right? And then on this side, we have 2P4 yields P4. Wait, I just realized we have to do it to the whole thing, right?
My laptop froze.
My laptop froze.
No, my laptop. Sorry.
Oh, okay. Okay, so in this case, we figured out what was being reduced and oxidized, and we know that that's how you do it now, right? Okay, wait. 1 second. Okay. Sorry, my laptop froze. Okay, so let's reduction was Cl plus 2 electrons was Cl minus, okay?
Yeah.
And then I'm just rewriting it so that we can see.
Okay.
Oxidation was P4 and then P4 plus 5 electrons. So I don't think we actually have to balance this part out because it doesn't include the whole reaction, right? Like remember when we were balancing them, like with the electrons, it was with the whole reaction, right?
Yeah, that's what I was thinking. I was like, we just took one out.
So I think that's why we only have to define the reduction and oxidation components.
Oh, but if you're to make a full equation, you have to use the HOCl and H3.
Yeah.
But then where did the PO4 come from? Like it would be like HOCl and then it would be like the arrow and then H3PO4. So there'll be like a random phosphorus on the other side for the reduction.
No. Well, it's 4P, right? And then it's O16. So that we're dealing with the P part alone.
Yeah.
So look at
I was just thinking like if we were to use everything. Yeah.
Yeah, but we're not. We're only asking for reduction and oxidation components. Okay, next we're gonna do a stoichiometry problem with titration. We have a somewhat hard stoichiometry problem that is multi-step. So it says that a student is given a wait, you can see the whole thing, right?
Yeah, I can see the whole thing.
Okay, so a student is given 1.08 grams of an unknown acid, H2A, and to determine the molar mass of the acid, the student titrates the sample using a 0.524 molar solution, and the balance equation is shown below. So if 35.5 milliliters of KOH are required, what is the molar mass of the unknown acid? So the first thing that I did here was try to figure out the number of moles of KOH, right? Because I have molarity and I also have the liters, right? So I know that 35.5 mil, and also you'll need a calculator for this. It's an FRQ1. So I know that 35.5 milliliters is 0.0355 liters, right?
Writing this information. Okay, sorry.
It's a 35.5.
Yeah.
And then I have 0.524 molarity. Okay? Right? And so since we're only talking about KOH right now, this only deals with KOH. So once you multiply those two things, so 0.0355 times 0.524, you get 0.018602 moles of what is it?
KOH. That's required.
Right, that's required, right? So if I know that it consumes the acid completely, I can use that for my reactants, and it's asking for H2A, right?
Would that be the limiting reactant because it consumes
because it's consumed completely, yeah. That's the only like the only information we're given, right?
Yeah.
So in order to figure out how many moles of H2A I can set up a mole ratio. So my mole ratio is 2:1, right? So what I'm gonna do actually is I'm gonna make this into actually I'm just gonna keep it like this. So 0.18602 mole of KOH, right? Times, and then I can set up the mole ratio, right? 2 mole of KOH times 1 mole of H2A. And so then you would get, these would cancel out, and you would end up getting that there are 0.09301 moles of H2A.
Yeah.
Now that you have this very crucial information, you can figure out what's the molar mass of H2A itself. So I know that I have 1.08 grams, right? So I'm going to set up a proportion here. If 1.08 grams of H2A is 0.09301 moles of H2A, and I'm trying to figure out how much is in 1 mole of H2A, I'm going to set it equal to X grams, right? Like setting up a proportion algebraically.
Yeah.
So if I do that, I get 1.08 equals 0.09301x. Divide both sides by 0.9301. And what would you get?
I mean, I just multiply. Oh.
100. So x equals 116.12 grams. But it asks for 3 significant figures, which is very important. So x equals 116 grams, or the molar mass is 116 grams. Okay. Does that make sense?
So I can't do 0.093 moles times 1.0 times 1.08 grams divided by 1 mole, because I'll just find grams, right? Not yeah.
I mean, you could do that if it works. Did you get?
I got 0.01.
Okay, no. Molar mass is usually quite large. And also you should know that it's not 0.01 based on that. If H2 is there, that's already 2.02 grams, right?
Yeah.
So you can just set up the simple proportion and that would work. And it should be 0.009 because this is 0.018 divided by 2 is 0.009 actually. But
Yeah, I put that in.
yeah, so 116 grams. So that was like a hard stoichiometry question. And then we can do another. Okay, so here is a kind of difficult stoichiometry reaction problem from an AP exam. So you can read the question, and the first question asks, what mass of CO2 is produced at STP? So we know that 44.1 grams of propane, and propane is C3H8, and 44.1 grams of oxygen are added to a rigid vessel. If you didn't know that propane is C3H8, what you can do is just take context from the reaction. There's only 2 things reacting, oxygen and propane. So obviously C3H8 would have to be propane. So what you can do is you can set up a simple stoichiometry, basically problem. So starting with A, I'll do the A portion first. So I have 44.1 grams of I have 44.1 grams of C3H8, right?
Yeah. Did I find
And
limiting reactant now?
yeah, that's what we're gonna do. We're gonna try to find the limiting reactant times 1 mole of C3H8, which is 44.1 grams of C3H8, right? And then mole ratio is 5 moles of O2 over 1 mole of C3H8, okay? And we know that that yields how many moles? Is that 5 moles of O2?
Yeah.
So if that's 5 moles of O2, right? Let's figure out how much O2 we have right now. It says that we have 44.1 grams of O2. So 44.1 grams of O2 times how many, what's the molar mass of O2? 16 times 2, 32 grams of O2 of 1 mole of O2. 44 divided by 32 is approximately, let's say, 1.4 moles.
Yeah.
So I needed 5 moles to run this reaction. I only have 1.4 moles. So that immediately tells me that O2 is my limiting reactant. So I'm gonna, are you okay with me erasing this?
Yeah.
The limiting reactant is O2. So I'll just put that over there. So now that I know that my limiting reactant is O2, I can run the reaction. So 44.1 grams of O2 times 1 mole of O2 over 32 grams of O2 times 1 mole of, let's see the mole ratio. Sorry, it's 3 moles, right?
Of what?
3 mole of CO2, because we're doing A, over 5 moles of O2, right? And then the molar mass of CO2 is 44.01, right? So this is the whole stoichiometry process. So let's scratch out everything that we got rid of. Grams, grams, moles, 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 moles. So once I do this, I figure out that I have 36.4 grams of CO2 are produced. Did you get that?
Wait, where did you get CO2 from it? Oh wait, I guess I'm really behind.
Okay, so we just
Oh
ran.
yeah, sorry, I got it. Yeah.
Okay,
Yeah.
so B is actually a very overcomplicated question. So remember how we figured out that the limiting reactant was O2? That already, yeah, go ahead.
Where did you get the 44.01 grams of CO2 from?
This is the molar mass of carbon dioxide.
Where?
Molar mass of carbon dioxide is 44.01.
Molar mass or grams?
Molar mass.
Oh, okay, sorry.
Molar mass is grams per molar.
Yeah.
Okay, did you get it?
Yeah.
Okay. So then, since we know that limiting reactant is O2, what would our excess reactant be? What is the other one? I can't read it. C3H8?
Yeah. I'm a little behind. Sorry. Oops.
Okay, that's fine. We can wait.
No, keep going.
Okay, so it says, what would the effect of doubling the mass of C3H8 be? So if you double the excess reactant, isn't that just going to produce way more excess? Right? So it would do literally nothing to the mass of CO2. So a way that you could phrase this would be doubling the mass of C3H8 would still keep O2 as the limiting reactant and would produce no change in the amount of CO2 produced. Is that good? Does that make sense?
That makes sense.
So now we have to figure out what doubling the mass of O2 would do. Well, if you want, you could run that reaction. So that would be 88.2 grams of O2, right? Times 1 mole of O2 over 32 grams of O2 times the same mole ratio and times 44.01 grams of CO2 again, because that's the molar mass, right?
Mhm.
So once you do that, you can figure out that it's literally just 72.8 grams. So what is the relationship between 72.8 and 36.4? It's a factor of 2, which means doubling the limiting reactant doubles the amount of product made. So you didn't have to run the whole stoichiometry problem if you noticed that, but I think it's a better way to confirm that it doubles the amount produced. So does this hard one make sense?
Yeah. So if I were to prove that doubling the mass of C3H would not change anything, would I just?
Yeah, because if you double the mass,
Yeah.
and
We
run
can talk about that. Yeah.
Yeah, so if you double the mass of, let's say you do 88.2, right?
Of O2.
And then you try, yeah, so double the mass of C3H8 propane, and then try to find the amount of oxygen created. You'd still figure out the oxygen, because if you double the excess reaction,
okay.
there's so much, right? So it has no impact on it. Okay, so hopefully that made sense. Okay, so here's another redox question. So we just have to figure out what charge is being changed. So Zn solid plus HCl AQ. I think there's a plus 2 HCl. AQ.
Sorry, can you hear my background? No.
No.
Okay.
And then ZnCl2 aqueous plus H2. Okay, so let's completely disregard the Ionic equation because that's not important when doing redox. Okay.
Mm-hmm.
So let's figure it out. So zinc by itself is 0, right?
Mm-hmm.
And then hydrogen is plus 1, which
Yeah.
automatically makes Cl minus 1, right? And then over here, if I know that Cl is minus 1, I know that zinc is going to be plus 2, right?
Yeah.
And then hydrogen is going to go to 0. Okay. So if I figure out what is being reduced and what is being oxidized, I can see that H goes from plus 1 to 0. So this is a reduction, right?
Oh, I thought this is an Ionic equation question. Oh, is this Stoichiometry redox?
I mean, you could do both if you want.
Yeah. Okay.
Okay, we can do it at the end then. And then what does zinc go to? Zn goes from
0 to plus 2, so it's losing electrons, so it's oxidizing.
Mm-hmm. And then to write that, you would include the electrons in the equation, right? So oxidized would be on the product side, right? So the electrons would be on the product side. Reduction, the electrons would be on the negative side, on the reactant side, sorry. Okay, so you also mentioned that we could try to make this a net ionic equation. So if we just disregard all the charges and oxidation and just, let's say, let the test ask us to just make a net ionic equation, which is overly simple, but so Zn has no charge. It's a solid, right? So it's just Zn plus 2H plus 2Cl minus, right? Hello?
Yeah.
Zn 2 plus 2Cl minus plus H2. Okay? Let's figure out what my spectator ions are. I can see that I have 2Cl on both sides. I'm going to get rid of them immediately. And I have my net ionic equation. Zinc.
This is a very dumb question, but would it be 4Cl minus or no? Oh, wait. There's not a 2 in front of ZnCl2?
No, there isn't.
Okay, sorry. Oops.
No problem. It's fine. Zn2 plus aqueous plus H2 gas. This is your net ionic equation. Does that make sense? Okay. That's all the time we have for today, but I hope that was helpful. Thank you. Wait,